again, ready to keep going. Let's see how this goes. So, let me continue from where I left off. I'm having a lot of, what's that called? Having a lot of drop frames. Dropping a lot of frames. What's going on? Okay. There we go, we're back. Alright, that was weird. Hello, hello, hello. I'm having a lot of, what's that called? What's going on? Okay. That was odd. Alright, let's keep going. So, I'm pretty tired, but also, I'm gonna try here. Alright, let's keep working. You have something to diffuse, time is running out. Your informer will provide you with a circular array code. Oh, you know what? There's something messed up, actually. Circular array, code length n, circular array, code of length n, and a key k. To decrypt the code, you must replace every number. All the numbers are replaced simultaneously. K is greater than 0, replace the ith number with the sum of the next k numbers. K is less than 0, replace the ith number with the sum of the previous k numbers. K is 0, replace the ith number with 0. Code is circular, the next element. Code of n minus 1 is code 0, the previous element code 0 is code of n minus 1. Given the circular array code and string k, key k, return the decrypted code. What? Oh boy, see if I can make it this far now. Alright. Ith number with the sum of the next three numbers. So these three numbers added together. Well, that's interesting. I should probably use a prefix sum to do this efficiently. How large can k be? It could be the size of the n, but n is kind of small. I think I'll still use a prefix array anyway. What is it? Says the previous k numbers. Actually, an easy way to do this is to use you double the array length for the prefix sum. So that way you don't need to do all the extra like arithmetic around circular logic. If k is 0, just replace it with 0, right? Okay. So we'll do that. We do threads also. Just get a prefix. I think this is correct, right? Yeah, 1 to 100. 200 numbers is fine, I think. And then we're going to say for constant x code. Actually, yeah. Okay. Actually, it should really be. I like this one better. Um, okay. All right. So we're gonna left to right create the prefix array, and we're not going to we're um we're not going to handle the circular logic. We're just going to iterate inside of the array more directly. Okay. So k is 0. We just say turn just return all zeros. We're going to say k is greater than 0. Otherwise, good. So we're going to say for int I 0 size size. Say code of I equals sum of the 3 numbers ahead, which is going to be prefix of I plus k is prefix of I minus. Um, could just shift this forward by 1. Um, hmm. It's actually the next three numbers. So these three, the prefix would be the sum all the way across minus prefix of I. So k is 3, right? So it's going to be 0, 1, 2, 3. It's actually just explicitly like this. And the same is true here. It's going to be the other way around. Minus k. So if we were going backwards from position 0, 1, 2, 3, we wanted the 3 behind. Or let's say it's the 2 behind. It's going to be the sum of these up to that point, minus 1, minus I minus k, which we say k, let's say k is 2, 0, 1, 2, 3, minus 2, 0. You can actually subtract 1 more here. When I is 0, this doesn't work as nicely as I'd like it to. I try. I need to get the prefix sum in the opposite direction, I think. Oh. That's a bit awkward. I gotta think about that. I think I can just add k here. So, not k, this is a little bit odd. Actually, I'm not sure if this is better than just handling the circular logic correctly. But the idea would be to just shift over to the right side prefix array. It's actually no real point in adding an extra 1 here. The reason why you shift over is that when you take the prefix difference, it still gives you the sum over the elements in that range, even if the prefixes are larger. So I think this does actually work correctly. Yeah, I think this is right. When I is 0, it's going to be code size minus 1 here. And I being 0, it's going to be code size minus 1 minus k. Which, let's say if there's 3 elements behind, it would be the last 3 elements, which is going to be, what did we say it was? Code size minus 1 minus I minus k, or no, code size minus 1 minus k. So like the n minus sum all the way up to basically the sum of the whole range. and then minus, so n minus 1 minus 3 would be n minus 2, n minus 3, n minus 4. That would actually give you only 2 elements, not 3. Is that right? N minus 2, n minus 3, n minus 4. So you'd have n minus 1, n minus 2, n minus 3. Yeah, no, actually this is correct. Yeah. This might just be correct as it is. No. Okay. It's pretty funny. All right. Oh, that's why. Right. Yeah. That works too. Okay, it's wrong. It's wrong. So minus 2. Oh, excuse me. There is an issue here. Subtle issue here. I don't know. I don't know if I got negative numbers there. I'm gonna go for it. This may or may not be correct, but I'm gonna try it. Oh, that's right. 100%. Okay, pretty good. Not bad. All right. How is the health? It's probably buffering a lot, I think. Yeah, it's not buffering too bad, but it is buffering quite a bit. Okay, I think that's reasonable. Not sure if I need to really explain too much about what happened here. Just quickly go through it. So thread local to reuse memory across test cases. If it's 0, we just fill. We're going to reuse the vector of inputs as well. So that one's pretty straightforward. Just fill with zeros. K is 0. It's an edge case. We're going to create a prefix array by basically iterating twice over the original array. So we're going to add values left to right and write them into an array that gets bigger and bigger. So it's going to go all the way across. And the reason we're doing that is you can use that to quickly calculate the sum over ranges and sum over ranges in a circular array. And it greatly simplifies the logic. So here's what the logic looks like in this case for the forward case. And something special and important here and special is that it's not the index plus k elements, it's the k elements after the index. So k elements to the right. That allows us to simplify this a little bit. If it wasn't like that, it would be a little more complicated. And I would probably need to, add code size. Excuse me, no, I wouldn't want to add code size. I'd want to modify this a little bit because I'm destroying the code array, so I can't easily reference it, which presents some challenges. But the way this was written, it allowed me to kind of make this a little bit easier. It'd be a little bit trickier because I'd probably need to like shift this over one element and put a 0 in the front, which makes things a little more complicated because then this code gets shifted over. Oh, this code is already, the second loop is already shifted a little bit. Anyway, so. Yeah, and then the second iteration, we're going to go backwards. So obviously, k is the number of elements. You just negate k, so we have a positive k to work with. And then we're going to start from in the prefix array, we're going to start from the second portion of it and go backwards rather than the first portion go forwards. So that's what's going on here. That's the shifting. It's very clean. Sort of very clean. I'm not sure if that's better or worse than handling the circular cases. Circular things can be challenging to deal with because of the like the way loops are set up. You kind of have to like tend to have to break circular things up into multiple loops. It makes things a little more complicated. In my opinion, it's not fun. Minimize string length. Okay, given a string S, you have two types of operations. Choose an index I in the string. Let C be the character in position I. Delete the closest occurrence of C to the left of I if it exists. Choose an index I in the string. Let C be the character in position I. Delete the closest occurrence of C to the right of I if it exists. Your task is to minimize the length of S by performing the above operations 0 more times. Return 0 during the length of the string. Okay. Let's look at these test cases. 100 letters. Sometimes the test cases explain a little bit better what's going on. 3, we choose I as 1, so C is A. Then we remove CS2. It's closest A character to the right of S1. One more time. Index C be the character in position I. Delete the closest occurrence of C to the left of I. Okay, so it shows I as 1, which is A. And then the closest one left is here. Oh, and this is the closest to the right is this one. I thought it said to the left. Oh, we have two types. Okay, we can go to the right or to the left. Okay, minimize the length by forming 0 more times. Doesn't this just remove the unique values? So we're just left with ABC, right? And CBD and yeah, I mean basically you just count the runs of characters left to right. So could do something with the following. I kind of like double for loops for this sort of thing, but double for loops are not always the best. I think it's just that simple. Yeah, I think we may not actually need this. I'm assuming this is correct. Okay, it's wrong in this case. So we should get 1, 2, 3, 4, 5, 6. Oh, they don't need to be. Okay, never mind. Never mind. This is actually much easier than I thought. I was going to say that I thought it was counting the runs, but actually this is just counting the number of unique characters in the string. So we'll just say int or bool has or contains scene. Scene is fine too. something like this. It's taking a minute there. Okay, I'm gonna go for it. This is fairly simple. Yeah, this is a fairly simple one. I should be able to get 100% on this. Nope. I might want to make that thread local. There we go. I was gonna say it should be 100%. Let's see if still getting a little bit of buffering here. It's not too bad. Oh, hard. Okay. Build a matrix with conditions. All right, the hard questions are much harder than the other ones. Positive integer k. You're also given 2D integer array row conditions of size n, where row conditions y above and below, and 2D integer array column conditions of size m, column conditions left and right, and two arrays usually contain integers. Okay. Have to build a k by k matrix that contains each of the numbers from 1 to k exactly once. The remaining cells should have the value 0. The matrix should also satisfy the following conditions. The number above should appear in a row that is strictly above the row in which the number below appears for all I from 0 to n minus 1. Number left should appear in a column that is strictly left of the column at which the number right appears for all I from 0 to n minus 1. Return any matrix that satisfies the conditions if no answer exists. Return empty matrix. So example 3, 0, 0, 0, 1, 2. K is 3, row conditions 1, 2, and 3, 2. So 1 has to appear to the left. Row conditions, column conditions. So 1 appears above 2. 3 appears above 2. 2 appears left of 1. 3 appears left of 2. Okay. Valid example satisfies the conditions. Okay. That's what they're looking for. All right. That's fairly simple. This, I think, is not actually that hard, by the way. Yeah. An interesting question. This is these conditions and these conditions, they represent, and being k by k, but only needing to put k elements in, means we have the freedom to basically select where we're going to put. We can do both of these sort of two-dimensional cases. We can do them in one dimension, each in their respective dimensions, which is very nice. It's basically like it's like a topological sort, more or less. So we would want to figure out what the sorted order for k should be or could be. All the values of k in each dimension, and then basically place them in their respective rows first, and then in each row you could choose where they belong in each column. So it's going to be I think it's called a topological sort. Yeah. Ugh. I think it's a topological sort. I just don't remember exactly how to handle a topological sort. I think this 1, 2 has to come. Yeah. Yeah. Okay. So 1 comes before 2. Sort of like 1 is less than 2. And then 3 is also less than 2. So you just have to have 1 and 3 placed before 2. So for a topological sort, basically you would start with nodes that have 0 inbound edges. And this is like a directed topological sort. 0 inbound edges. Prune them, use them, basically put them, and it doesn't matter what order they're in. And then remove them and the outbound edges, and then the nodes that they connected to. You would check and see what their inbound degree is. It's called the degree of the graph. Just trying to think, like, how do I apply that here exactly? I would say I think I'd want oops, shoot, no. Oh, shoot, didn't do that. The values of k are between 2 and 400. Okay. So what I might want to do is for each value of k, basically create an adjacency list, convert this input into an adjacency list. And the reason I'd want to do that is when I'm processing a node, I'd want to check it for all of its outbound edges. Efficiently, quickly. Yeah, it's probably fine. A pre-processing step to do that's probably fine. Adjacency list is probably fine. And then have the degree for the inbound edges for each of these as well. Okay, we can do it that way. I could try it that way. So let's create the adjacency matrix as well as the inbound edges. We'll do it for each one. We'll do it thread local too. See how that works. So say adjacency matrix or adjacency list. Okay. And just clear those vectors. Okay. We're going to go through. The other one is the adjacency list, and the second one is the inbound edges. This actually doesn't need to be a vector. Vectors could be an array of vectors, which is a little bit unusual. This could be an array of bound edges. Okay. Then we're going to clear. We could just do in degree. In deg is probably better. Okay. So, yeah, as we start off, we probably just clear those things. And then we say for each of the row conditions, is that right? Row conditions. Say indeg plus indeg of, really it would be the second element, and the adjacency list of first element, push back second element. Okay. Now this is what we're going to do for the column conditions too. Pretty much exactly the same thing, but we're going to do that after we process the it looks like, oh wait, oh excuse me, process the row condition. Yeah, we're going to do the column conditions, and then we're going to do the row conditions. We'll do the row conditions first. Okay, so we do the row conditions, and the way this is going to work, it's going to be the row sort, I suppose. So the row positions of size k. This also could be thread local. Come back to that. Okay. So defining the row position, we're going to say for inbound degrees. Start with sort. Or actually, yeah, I mean, so for int size 0, I is less than, let's actually create a queue. Of stack. 0 degree. And we're just going to reserve k. So I is less than 0, I is less than k. And I, if in degree I is equal to 0, then you don't even need this actually. Just say int current is equal to k, and while current is greater than 0. Perform while loop. Oh, I see. Yeah, we do want to go to 0 degree. Forgive me. We do want to do that. Okay, hold on. Okay. Now we do a while loop. So while we have 0 degree elements, we're going to say for each int I is 0, it's less than degree dot size. Increment I, we're going to have step vector. Next level. It's like a level or traversal. But I would say so the node 0 degree node. What we're going to do is the adjacency list. Say child, the adjacency list of the node. We're also going to push into row position. Let's do a row index. So if it's 0. So first things first, row position, row index is equal to node, and increment the row index. Next thing that's going to happen is for each child, we say in degree child decremented. If in degree of child is equal to 0. 0 degree is the next level. Dot push back child. Okay. Then say 0 degrees not empty. And keep going. Okay. This will create the row position sequence. And then we just do the same thing down here, except for the column sequence. Column position, column index. This could probably be its own function that I do this in, but I'm going to use duplicated code for now. Okay. And then when that's all done, then I can say the matrix that I'm going to return looks like the following. We're going to say for I, so I should have a row 1, and then it'll tell me which value is in that row. And then I should also see which column, which column that value in row 1 should be in. I didn't think this all the way through, did I? I think I missed something important. Let's see. So the tricky thing here is, give me one moment. I'm gonna just kind of close my eyes for a minute. Just kind of think about this. Excuse me. think I did this slightly incorrectly. Yeah, I made kind of a mistake, slight error. I need to know which column that this value is going to be in. Okay. Kind of need to take the inverse, column inverse. Okay. By the way, these could just be K instead of 401 each time, but we'll leave it for now. I made a slight error. It's recoverable though. Made a mistake, but it's recoverable. So I need to know where the value that's going in the first row, where it is in the I basically need to invert. I need to invert the column matrix or column array. So column invert is going to be so it's going to be column inf is equal to I of column what is that, position, column position. Yeah, so it'll be right. So this will tell me where I'm putting each value, each node in the column positions. Actually, I could just reverse this right here. Do column inverse is equal to node column index. That's actually what I need. Yeah, it's probably fine. It seems a bit odd, but I think it's right. Okay. We'll just do column inverse directly. I don't need to do this part. All of these can be optimized slightly to be just plus K instead of plus 401. Oops. Okay. So we're gonna say int size 0. Actually, in this case, it should probably be equal to K. Yeah, these are integers from 1 to K. Yeah, less than or equal to k. Should be equal to k in these cases. Less than or equal to k, rather. Okay. Yeah, and then we would say result of the I. So the row position of I and the column inverse of I. Yeah, so, right. Um, Actually, I think both of these should be inverted. Yeah, these should actually both be inverted. I don't know how I got that wrong. Yeah, I totally got that wrong. And that's, yeah, I think that's it. It's that simple. How are we doing on a lot of buffering lately, man? Time error. Hmm. Oh yeah. So do this for the row conditions. Then we do this for the column conditions. Hmm. Mm-hmm. Okay. What values did we get for inverse column inverse? All right, so it's been 1 hour. Do 3 more hours. Try to do about 3 more hours. Okay. Got a runtime error now. Hmm. 1030. I'm missing something important here. Yeah. Which this sort of thing happens when you don't you duplicate code. It's pretty typical. Yeah. You should really start off at 1, I think. Quite frankly. It's also kind of subtle. It might matter. A lot of buffering. Oh, okay, it did matter. Interesting. Cool. And what's this? Wait, what? Oh no. Don't tell me. Don't say it ain't so. Say it ain't so. If no answer exists, return empty matrix. Oh no. Okay. Uh-oh. Uh-oh. So, gotta do cycle detection. I didn't even think about that. I didn't even think about that. Okay. Yeah, it makes things a little more complicated. But I should be able to handle that. So the way cycle detection works is basically you're gonna see if this actually came out pretty good. The way cycle detection works is if the topological sort fails, so what can happen is there are no 0-degree nodes anymore, but the row index is less than k. So it should start off at 0 and end up at k. If row index is less than k, return empty. And same thing here with column index. That means there is a cycle. Oh, there is a subtle difference between a vector with an empty vector, single empty vector, and a vector that's just totally empty, which is interesting. That's what they were looking for there. Okay. This looks like it's probably correct. I'm going to go for it. There's a slight chance it's wrong. This took me a while to program if it's correct. If it's not correct, I still have more to go. Okay, looks like it's correct. That's great. On the faster side, sweet. Yeah, it took a while. I probably could have done a better job. I was kind of trying to do like preemptive micro optimizations. I also kind of missed. They were looking for the cycle detection as well. If I run it a few times, I should be able to get the. Oh, there we go. 100% runtime. All right. 100%. You can't beat 100%, can you? So, or can't beat 0 milliseconds, can you? So we'll go with that. I think hopefully I explained what I was doing there reasonably well. Maybe that was a LeetCode hard. I should explain what that was. Let me do that. See how we're doing with regard to buffering. Yeah, it's still buffering a bit. Okay, so let me explain it quickly, briefly. So, oh man, it's taking a while, huh? Oh boy. No, man, it's really taking a while. Hold on. Is everything okay? What is happening? There we go. Okay. That was weird. All right. So let's talk about it. It's positive integer k, you're given row conditions and column conditions. What this means is that we're going to put elements from 1 to k into a k by k matrix, and we need to have the above element. It's going to be in the rows. It's going to be above the below element. So if this is like a 5, it's got to be above. If this was a 3, it would be 5 would appear above 3 in the final result, in the final matrix. Same thing, left side and right side. So if there's like a 6, it's got to be to 6 and a 2. 6 has got to be to the left of the 2 in the matrix. And they kind of explain this in a little more detail here. And if there's no answer, which can happen if their conditions conflict, if it's contradictory, then it's an empty matrix. So they give an example of a matrix with 1, 2, 3, case 3. Conditions 1, 2 means 1 has to be above 2, and 3, 2 means 3 has to be above 2. Same thing for the columns. 2 is to the left of 1, and 3 is to the left of 2. So as it turns out, one approach to this problem, one solution, is to use topological sort in each dimension. Since it's a k by k matrix and you only have k elements to place, you can place every element in any spot in a particular row, or any column in a particular row, or any row in a particular column, and you'll be able to satisfy each of these conditions independently. Because you basically have you have k different slots to pick from, so you can always fit them wherever you want, basically anywhere wherever you need them. So anyway, a topological sort based off of the order that's created by each of these conditions, and you basically just do it each of them independently, as I mentioned. Allows you to create a basically like which row should this particular value be placed in, and then which column should it be placed in. And you can get those two different topological sequences and pretty much just merge them. As I mentioned, because you have enough space, you can merge them pretty easily without conflicts. You can guarantee there's no conflict. The issue you run into here if you do it this way, though, is you do have to check using your topological sort whether or not you were able to place every element, whether or not you were able to basically you didn't have any circular logic in terms of the conditions, which actually the topological sort can figure that out efficiently. In this case, can do it efficiently. So that's what's going on here. Yeah. And the code is kind of complex. Maybe more complex than it needs to be, but the basic idea is there. A lot of zeroing things out and setting things up. And I use like a level order traversal style approach to the topological sort. If you're curious about how to process the topological sort, you keep track of the inbound degrees of the vertices, and you dump all of the zero inbound degrees into a like a queue, process all of them, and then as you process them, as you remove them from the graph, you would also decrement their children, right, where they point to, decrement those by the point, by one, really, for each one. And then if each of those end up being zero, any of those end up being zero, put those into the queue that you're going to process again. And so you end up with sort of a level order traversal where you process all the 0 degree nodes, 0 degree vertices, one layer at a time. And you dump each of those nodes into this data structure that'll tell me where that node should be in the rows. And it's basically symmetric code for the columns. One upside to this is that when it's done, figuring out whether or not there was a cycle is as simple as counting how many vertices did you process, which in this case I've got this row I of x, row index, which keeps track of that. So if you didn't process all the vertices, that means there was an issue. Yeah, pretty straightforward overall. Like I said, I have some duplicated code, so I could have made this actually like half as long. But I didn't. Just copy pasted the code. Copy pasted the first half of the code again to create the second half. I'm really tired, man. I'm exhausted. Holy smokes. So there you go. That's this question. Not too bad. And let's move on to the next one. Yeah. How are we doing in terms of? It's only been an hour and 15 minutes. Oh man. It feels like it should have been like 2 or 3 hours, or I still have 3.5 hours, over 3.5 hours, 3 hours, 45 minutes. Am I gonna make it that long? I don't know. I might make this just 2 hours and go to sleep. I'm pretty tired already. The lexicographically smallest string after applying operations. Okay, given a string S of even length consisting of digits from 0 to 9 and 2 integers A and B, you can apply either of the following 2 operations any number of times and in any order on S. Add A to all odd indices of S, 0 index digits post 9 or cycle back to 0. For example, A is 3, 4, 5, 6. 8 plus 5. Excuse me, 3, 9, 5, 1. Okay. So add A to the odd indices. And rotate S to the right by B positions. S is 3, 4, 5, 6, B is 1. It rotates to the right. Okay. Return the lexicographically smallest string you can obtain by applying the above operations any number of times on S. Okay, so odd indices. So you can add the a to the odd indices, perform one rotation, and then add a to the odd indices again, and that allows you to add a to all of the digits. So you add a to all the digits as many times as you want, and you can rotate as many times as you want. But you also might just want to add a to the odd indices, or just add to the a to the even indices, and rotate. So there are three options here. Add a some number of times to the odd indices, add a some number of times to the even indices. And then rotate to the smallest value. That's interesting. Yeah, you can add a to any number of times to the even or the odd, two different amounts, arbitrary amounts, and then also rotate to get the smallest. And then with the lexicographically smallest string. This is an interesting question, to say the least. Two integers a and b. What are the constraints? A and b. A is oh, excuse me. You can't. No, I was wrong. You can't rotate entirely. You can only rotate b positions. Okay. So it's a little more complex. Okay. I'm so tired. I don't know if I'm gonna be able to go that much for longer. I'm kind of exhausted. I'm pretty tired. And it's buffering a bit. My leg is killing me here. Oh, man, I kind of overestimated how long I'd be able to sit for. I don't know. I'm thinking about just taking a break here. I mean, there's no real reason for me to. I have to think about this a little bit more anyway. Oh, excuse me. Yeah, I have to think about this anyway. All right. I'm really tired. I'm like falling asleep. Let me actually stop here. I was gonna do 4 hours, but I'm having a hard time doing that. I'll just say thank you for watching and stop here. Like I said, I'm exhausted. I'm so tired. All right. Let me change the title. It's like, yeah, I gotta stop here. I'm so tired. Okay. We'll just say thanks for